In this video, we are going to discuss the Wittig reaction. This is a very powerful reaction. We use it quite a bit in synthesis. And what this allows us to do is this allows us to take an aldehyde or a ketone. So here we go. Here's an aldehyde. I'll put in parentheses an R group for a ketone, so an aldehyde or ketone. And we react it with what we call a Wittig reagent. We also call it an ylide. And that looks like this. All right, so this is the Wittig reagent or an ylide. And what we essentially will end up making is an alkene. So we end up generating this here. Right? So we end up generating this and then triphenylphosphine oxide as a byproduct. So to summarize, we take an aldehyde or a ketone and we end up generating an alkene. So this is a very powerful tool that we can use in synthesis. Now, before ever knowing anything about the mechanism, you can figure out what the product's going to be because it's pretty straightforward. So imagine this. I'm going to take this highlighter right here. All you're really going to do is you're going to take this carbon right here and everything that's attached to it and put it in the place of the oxygen and literally just replace the oxygen with that carbon to get to the product. So without knowing anything about the mechanism, you can easily figure that out, and you see it right here. Right. So that's as simple as it is, and we'll go through the mechanism in a minute. But to be able to answer these questions quickly, you should be able to see that, right? So I can give you a sample one here. So why don't you try this one, right? So here's a ketone, and we're going to react it with this ylide. Right? So go ahead and pause the video and see if you can form the product there. All right, so if you're able to form the product, then again, all we're going to do is replace this oxygen right here with the carbon and everything that's attached to it. So if we do that, then the product is simply erase that oxygen and put the CH3. Here's our product, right? And again, the byproduct in this case is triphenylphosphine oxide. This byproduct is important, and we'll talk about that, the reason for that, in just a few minutes here. All right, so now let's talk about this ylide. Let's go ahead and really dissect this part right here, this active reagent, so we can understand how that mechanism is going to behave. So when we do this here, uh, so here is the ylide. So I'm going to draw it in its very long form here. Because we notice that there's 3 benzene rings or 3 phenyl groups that's attached to it. So I'm just going to draw this out so you get an idea of how big this molecule really is. So here is the molecule. So again, 3 benzene rings attached to it. And then we have a carbon, and I'm going to utilize this one up here. Uh, we have a carbon with a negative charge on it, right? So this is what it looks like. As you can imagine, that takes a lot of time to draw out. So we just simply say that this is the same as this, right? We abbreviate the benzene rings with pH, and then we have a negative charge here and a positive charge here. This is what we call an ylide. When you have a positive and negative charge on adjacent carbons, that's what we call an ylide, right? So positive and negative charges on adjacent atoms. Now you should also realize that there is a resonance structure here. We can push these electrons here to form a carbon-carbon double bond, or sorry, a carbon-phosphorus double bond. So if we were to see this, and I should use my resonance arrows here, if we were to see this, we should realize that they're the same thing, right? So any of these structures can be used interchangeably. All right, so now let's go through the mechanism of how that works, okay? So let's do this. Let's do mechanism. All right, so when we do this mechanism here, we have a ketone, and we're going to have our ylid. And I'm going to use this ylid here. All right, so again, a negative and positive charge on adjacent carbons. Now again, don't worry about what you don't know, worry about what you do know, use it to the best of your ability. Where's the most nucleophilic atom, do you think? It is the carbon, right? The carbon is with the negative charge is the most nucleophilic atom. Where's the most electron deficient atom? It is the carbonyl carbon. Very good. So we can push our electrons here, and this is going to come and attack that carbon. You form a bond to that carbon, you better break a bond. Now, you instinctively may want to put the electrons on oxygen, right? But right now there is an atom that wants the electrons even more than oxygen, right? Which atom is that? Which atom wants the electrons even more than oxygen? Yeah, that phosphorus. This phosphorus is positively charged, right? So the electrons in the pi bond can come and attack that phosphorus. And what we ultimately end up making here, students would call it a square, right? Well, we can be a little bit more specific. It's not a square, more so than what we call an oxaphosphatane, right? So here's what we end up generating. And this is what we call an oxaphosphatane intermediate, right? Oxaphosphatane intermediate. Now, so when we do this here, um, the products that we end up generating are an alkene and triphenylphosphine oxide. Now, with that said, I'm going to draw this. I realize that my bond angles are going to be a little off, but I just want to draw it this way so that you can see if you can visualize how this is working here, right? So if here are the products, again, I realize my bond angles are not correct, but I just want to see that you can see what is forming here, right? So these are the products. So we end up forming our alkene, which we see here, and then we also end up forming our byproduct here, which is our uh, triphenylphosphine oxide. So how would you push your arrows here to get to this? So why don't you pause the video and see if you can push the arrows to get to the final product over here. Hopefully you notice that all that's going to happen is that they switch partners, right? So that means that these two electrons are going to come here to form that phosphorus-oxygen double bond, and then these two electrons are going to come over here to form the carbon-carbon double bond. So it's just a switch, right? So we can see that happen here. Now, so here's the question. So we end up forming these two products here. We have our alkene, and we have triphenylphosphine oxide. So let's see what you remember from watching, from going through your Learn Smarts. What is the driving force for this reaction, right? What is the driving force? What pushes this reaction to proceed? So go ahead and pause the video and pick from the answer choices here. What is the driving force for this reaction? All right, so hopefully you answered that it is the formation of the phosphorus-oxygen double bond, right? Formation of the phosphorus-oxygen double bond is the driving force. This is a very strong bond. It's very stable, and there is a biomolecule, right, that is in our bodies that is made up of phosphorus-oxygen double bonds, and that is what, my biology colleagues, what would that be? Yeah, that's DNA, right? DNA is made up of phosphorus oxygen double bonds. The backbone of DNA is phosphorus oxygen double bonds. And that's one reason why DNA is so stable. You can imagine when there's a crime scene, right? Even if it was years later, if they found some blood or some type of biological fluid where they can extract DNA, they would be able to because it's very stable, right? So phosphorus oxygen double bonds have that strong stability, right? That's also another way, and you'll learn this when you take biochemistry. When we talk about protein inhibition, that's also a mechanism of how nerve gas works. which was used as a biological warfare, or chemical warfare, I should say, where it binds proteins, acetylcholinesterase, by inhibiting them irreversibly through phosphorus-oxygen double bonds. So yeah, these are very strong bonds, and this is the driving force for this reaction. Now, we also want to mention that there is limitations in this reaction, right? There's some limitations. So if we were to try this reaction here, and to get a product, what you might realize, all right? So let's say I said, give me a product. Go ahead and give me the product. Pause the video and give me the products of this reaction. Well, if you pause the video, you might just, again, just like we said before, take this and replace it with oxygen. You'd end up with this. However, this drawing doesn't really depict what we end up generating, right? Because we're neglecting something here. We're neglecting stereochemistry. So what this actually ends up being more like here, right? This is, if we were to draw out what they look like, we have two possibilities. One is where we have it drawn like this, right? This is the trans isomer. And the other is where we have it drawn like this. Right? And this is the cis isomer. So the limitation here is that we end up generating a mixture of cis and trans isomers. That's the limitation. And if we wanted to see, it's about 59% trans and 41% cis. But the truth is, it's really hard to tell which one is going to be the major product. It's not until Organic 3 that we'll really dive into what dictates which one's the major versus minor. So the purposes of this class, we're just going to say that there's a limitation is that we would produce both of these. Now, and it'd be very hard for us to predict, at least in this class, which one would be the major. What we'll learn in Organic 3 is that there are different types of ilids, some that we call stabilized ilids, some that we call non-stabilized ilids, and that can dictate the percentages here. But we're not going to go through that much depth in this course. All right, so that's the Wittig reaction. I hope that at least helped as a review from your Learn Smarts and from your reading. And if you have questions, again, feel free to email me or contact me or visit me during office hours. Until next time.